All right, hello again, everybody. Today we're going to be talking about some polynomial functions. And so first, we're going to review what polynomial functions are. So what we're concerned about is a polynomial function in one variable. And so it's an expression of the form a sub n x to the n plus a to the n minus 1 x to the n minus 1 plus those are just going to be terms in between there, so it can be as many terms as necessary. There we go, plus a sub 1 x to the first plus a sub 0 x to the 0. So let's notice a few things here. These a sub n minus 1, a1, and a0, these are all just going to be numbers. So there will be something like x squared plus 7x minus 3. Here we have a 1 out in front of the x squared, and so this would be what these a sub n's are representing. They're just numbers. This is just the scientific definition of what a polynomial function is. Something to note about these are that a sub n, the leading one, so this one over here, cannot be equal to 0. And the rest of them, your a sub n minus 1, a sub 1, and a sub 0, just all have to be real numbers. They can't be complex numbers, so no i's. So no i's for imaginary numbers, that is, I should have specified. A sub 1, a sub 0 are real numbers. And then lastly, the exponent here, our n minus 1, and however many exponents we have to be positive. They cannot be negative numbers. So we can't have anything like 1 over x, because that's the same thing as x to the negative first, and this is not a polynomial function. That's a different sort of function. So you need to have positive exponents. Additionally, you can't have anything like xy squared plus xy plus 2y, because this has two variables, and we're only looking at polynomials in one variable. So there only needs to be one variable for what we're concerned with. And then just a quick recall that polynomials are in standard form when the values of the exponents are written in descending order. So we've been talking about this, but just real quick, if we had something like negative x squared plus x minus 2x cubed plus 7, that's not in descending order because the 3 is our largest exponent here, and it doesn't come first. So how we would rewrite this is negative 2x cubed. Now we'd look for our next highest exponent. In this instance, it's 2. So then we have negative x squared. There's a 1 attached to this x plus x. And then our constant over here, plus 7. So make sure to write the polynomials in descending order for standard form. Now we just have another quick recall. We've gone over this before as well, but we've got the degree and the leading coefficient of a polynomial. So the degree of the polynomial is the value of the biggest exponent. So if we had something like what we just had, negative x squared plus x minus 2x cubed plus 7, the degree is the value of the biggest exponent. So here, our degree is 3. And then the coefficient of the first term of a polynomial in standard form is called the leading coefficient. So last time, on the previous slide, we put this polynomial into standard form. There we go, over here. And the -2 was our leading coefficient. So -2, since it's the value, since it's the coefficient of the first term in standard form, that's going to be the leading coefficient. So leading coefficient, LC, is -2. So a new idea we're going to introduce today is the idea of a relative maximum and a relative minimum. So a relative maximum is where there are no other points nearby that have a greater y coordinate. So what this means, so I'll do relative maximum in red here. That means we've got some sort of graph that looks, it could look something like this. We'll call this the y-axis and this the x-axis. This point right here would be what's known as a relative maximum. Because no other y point is greater than this point. And so some characteristics of that are it looks somewhat like a mountain. It's the top of a mountain. And you can think about it as if we're going along our function this way, it increases when we're moving towards the point, and it decreases as we're moving away from the point. Now, if we think about the opposite of relative minimum, it's when no other nearby points have a lesser y coordinate. So I'll do that one over here in blue. So that'll look something like this. And again, I'll draw in our x and y coordinate plane. So here, our relative minimum would be this point, because no y coordinates have a lesser value than that one. And so just like with the relative maxima, we can characterize this one. So this looks like a bowl to me, or if you want to keep the nature theme, it could be like a valley. And so as you're moving towards that point, your function is going to be decreasing, but then it'll be increasing the function as you move away from the point. So let's take a look at this graph over here. So if you look at it, we've got two quick questions here. So how many real roots does this polynomial have, and does it have any relative maxima or relative minima? So relative maxima, if you notice last time I used maximum, this maxima right here is just the plural form of maximum. And same with minima, that's just the plural form of minimum. So it's still asking us to find a relative maximum or minimum, but it's also keeping in mind that there could be multiple, because we can have multiple relative maximum and relative minimum. So if we look at the graph, so it asks us how many real roots does this polynomial have? Well, that's where it crosses the x-axis. So we have a real root here, a real root here, a real root here, and a real root here. So there are just 4 real roots. So 4 real roots. I'm using RR. Now let's look for the maxima and minima. So the maxima, we'll do that first. That'll be in red over here. That's where no x value is larger. Sorry, no y value. I misspoke there. It's where no nearby points have a greater y coordinate. So if we look on this graph, the only place where this happens is this red point up here. And we're only focused on the nearby y points. So we don't care about the points off over here or off over here. It's just around this point. So it looks like we have one relative VE maximum. And then let's look for the relative minimum. Well, it's the same thing, except for we're looking for this place where there are no lesser y coordinates. So we're looking for our bowl here. And in this instance, we've got one over here and one over here. So you can have multiple maxima and minima. So here we have 2 relative minima. M-I-N. See, I can't spell today. Two relative minima. And so if we just think about our maxima again, we were increasing as we were getting towards that point and decreasing as we got away from that point. And likewise with our minima, we were decreasing towards the point and increasing away from the point in both instances. So that's a good check on if it's a maxima or minima in a given graph. So let's look at this next one here. So it's this red line right here. It might be a little hard to see, but we're focused on this line. Here's our x-axis, and here's our y-axis, just to make sure that we're all on the same page here. So how many real roots does this polynomial have? Well, it doesn't cross the x-axis anywhere. So this has 0 real roots. But then let's look. Does it have any relative maxima or minima? Well, this value is just a constant along. It's just a constant, actually. It doesn't change as we're going along the graph. So every point is the same as the last point. That means that there are 0 maxima and 0 minima. Because when every value is the same as the last, no one value is greater or lesser than another value. So now it's going to be your guys' turn. So I'm going to show a few graphs, and I'd like you to see if you can determine how many roots the polynomial has and how many relative maxima or minima the polynomial has. So I'm going to keep each graph up on the screen for a couple seconds. Feel free to pause the video. Go ahead and try it. I encourage you to do it. Of course, you could just skip to the end for the answers because I'll provide answers and a quick explanation at the end. But I really encourage you guys to all do it because it's really beneficial for you in the long run. So here we go. Graph number 1. Graph number 2. Again, you can pause the video if you need more time. Graph number 3. Here's graph number 4. This one might be a little hard to see, but it starts down here and goes to up there. All right, so I hope you guys all tried it. So here are the answers. So graph number 1 has 1 real root, and there are no relative maxima or minima. So going back to graph number 1, we can see that it crosses the x-axis once at this value. It doesn't really matter what the value is, it didn't ask us. But since the line is just increasing at a constant rate, there's no point where there's one random point that's relatively larger or relatively smaller than any of the other points. Therefore, it's got 1 real root and none. No maxima or minima. So if we look at graph number 2, it's got 5 real roots, and there are 2 relative maxima and 2 relative minima. So, looking at our roots here, we've got 1, 2, 3, and there are actually 2 over here, 4, 5. And then looking for our maxima, again, this will be in red. We've got 1 here and 1 here. And for our minima, we have 1 over here and 1 right there. It's really small. So that's why graph 2 is that answer. So graph number 3 has 2 real roots. It's got 1 relative maxima, but no relative minima. So if we look at graph number 3, we can see the roots right here and the maxima at the top up here, but there's no minima. So you can have an instance where you can have a maxima or a minima and not the other. And then lastly, graph number 4 has 3 real roots. And then it has 1 relative maximum and 1 relative minimum. So if we look at graph number 4 here, the roots are here here, and here. And then we can see our maximum up here and our relative minimum down here. So on the homework, I'm going to probably ask you a few questions like this. So just keep that in mind. Keep in mind what we've talked about here today. And yeah, and identifying graphs is really important. And it's a skill that I think we should all try to develop. So there we go.